Light travels at exactly 299,792 kilometers per second. At that velocity, a single photon crosses a major city in a tiny fraction of a second, making it appear instantaneous to the human eye. This chart shows the precision of modern optics. Today, we confirm this speed using atomic clocks and complex laser setups capable of measuring light's movement over just a few meters. But measuring the fastest velocity in the universe was once considered impossible. In the 1600s, scientists lacked sensors, they had absolutely no electricity, and couldn't track exact seconds. To find the limit, early astronomers had to abandon Earthbound experiments. They turned to the solar system, using planetary orbits as the components of a massive natural laboratory. In the late 1600s, Ole Romer worked with telescopes that were little more than rudimentary glass lenses housed in wooden tubes. His research focused on Jupiter and its innermost major moon, Io. Io completed a full orbit every 42.5 hours, slipping into the shadow cast by Jupiter with the regularity of a metronome. After tracking these eclipses for months, Romer found that his predictions were failing. Depending on the time of year, Io would emerge from the shadow up to 20 minutes late. Romer concluded that the moon's orbit was stable, which suggested the 20-minute lag was happening during the light's journey from Jupiter to the observer's eye. The delay was predictable, tied to specific months when Earth's own movement changed its relationship to Jupiter. A top-down view reveals the geometry behind the anomaly. The Sun sits at the center, surrounded by the paths of the planets. Earth completes its inner orbit significantly faster than Jupiter travels its outer ring. At certain points, Earth moves to the far side of the Sun, creating a massive spatial gap between our telescopes and Io. Romer realized the visual image of the eclipse was simply traveling a longer distance to reach the observer. This 20-minute lag represented the time light required to cross that additional span of space. To find the actual speed, Christian Huygens needed to quantify the extra distance the light had traveled. Astronomers used the distance between the Earth and the Sun, 1 astronomical unit, as their baseline. When Earth is on the opposite side of the Sun from Jupiter, the extra distance light must travel is the full diameter of Earth's orbit, or exactly 2 astronomical units. Huygens divided that known distance, the 2 astronomical units, by the 20-minute delay Romer had recorded. His calculation yielded a speed of roughly 220,000 kilometers per second. Although early estimates of the astronomical unit were less precise, the math provided the first definitive proof that light travels at a finite speed. This measurement replaced the ancient assumption that light traveled across the universe instantly. Romer and Huygens proved that humanity could solve universal laws without high-technology sensors by using the geometry of the planets as a laboratory. Because light requires time to move across space, the images of stars we receive are actually delayed. When we observe a celestial body, we are seeing it as it existed minutes, years, or even centuries ago. Every time we look at the night sky, we are looking back in time, a reality identified because a moon around Jupiter was 20 minutes late.